Here's lecture number 17, the one you've been waiting for, the final one. In this lecture, we're going to be talking about implementation issues associated with robust tracking. So I'm going to talk a little bit about implementing the ripple-free deadbeat design and how also to deal with disturbances. So that's an additional thing we're going to be talking about. So if you remember back at the beginning of this course, here were the promises I made to you, that at the conclusion of this class, you should be able to do three things. Develop a math model for any given linear system, design a controller for the math model that effectively meets a set of specifications for that system, and three, implement the controller design on actual hardware. So you've been kind of gearing up towards this one, but there are some more issues we need to talk about in order to actually do this kind of thing. So these two we've talked about. In terms of developing a math model, we had a number of things that we were looking at in terms of developing math models. We had the analytical approach, we had the empirical approach. Analytical approach basically was based on the laws of physics. The empirical approach is based on system identification. In terms of our control design, we had numerous designs possible. We primarily focused on ripple-free deadbeat design. That's because it allowed us to do performance, robustness, and tracking. And we're also going to talk a little bit about disturbance rejection as well. So pretty much all the kinds of things we would want, we can do here. That doesn't mean it's a perfect controller. There's definitely limitations, but it is a good place to start. So again, for the tracking model, for example, suppose we wanted to track a sinusoid. So this is a sinusoid, and here's the Laplace transform of that. Again, in order to track this signal, we need to introduce a tracking model. So the tracking model would be of this form, some numerator polynomial divided by the denominator being the same as the reference. And so the numerator can either be a constant or can be set up to cancel poles. And so in our controller structure, then, we introduce our tracking model. And so all of this in here is digital. All of this out here is analog. But the question is, how do we do this analog thing over here? Because I actually need something with a very specific analog transfer function. So there isn't a nice, handy way of doing it. We can't just make a SIMULINK block to do this thing, because this is analog. Okay, and so even though the computer can simulate analog things, it actually does so digitally, and we'll come back to that. So how would we actually create an analog model? Well, if, for example, I had this model that I was trying to work with, so here I have a second-order polynomial over a third-order polynomial, so I have an S, and then this is a sinusoid type of thing. So this is a kind of model we might want to do where this would be used for tracking a DC offset sinusoid, which is actually, if you're going to track a sinusoid, you actually probably want to do a DC offset sinusoid. So anyway, this is the transfer function that we would work with. Here is an analog circuit. So we talked about analog circuits before. This is an analog circuit that can be used to realize this transfer function under these assumptions. That is, the coefficients A0, A1, and A2 are all between 0 and 10. Omega is between 0 and 31.6. It's like, where does that come from? Actually, that's 10 root 10. That's actually what that number is, 10 root 10. And then this condition that A1 minus A2 omega squared, that should be omega squared, is less than or equal to 10. So under these conditions, this circuit would realize that transfer function. And so notice that I only have two unknown values, R and C. And so I have multiples of, or rather fractions of R and C. And then where I have gains that may not be a function of C, I have, for example, A2 over 10. And so if you think of what this is, so remember, A2 is between 0 and 10. So this, as a number, is between 0 and 1. And so basically the wiper would be positioned between 0 and 1. 0 being all the way down, 1 being all the way at the top. Then the position of this is positioned proportionate according to this value. So this is going to be a value between 0 and 1. If A2 is equal to 10, then it will be all the way at the top. If A2 is equal to 0, then it will be all the way at the bottom. otherwise it'll be somewhere in between. And so we look at each of these gains that way, and so each of these gains are set up to be proportional to be a number between. So each of these conditions basically guarantees that the number is between 0 and 1. Okay, 0 and 1. So notice this is actually the same as the square root of 1,000. Right, so this circuit, we'll realize that. So it's a fairly complicated circuit, and again, it's, even though all the components are well known, it's still fairly complicated. It requires 1, 2, 3, 4, 5 op amps. So notice this condition here. Notice if this quantity in the numerator is negative, it turns out we have to change around the circuit so that we include another inverter in here somewhere, an inverter to invert that signal. And so those are some of the kinds of things that would, if these assumptions are not met, those are the kinds of things we would need to do. So for example, suppose one of these values is greater than 10. So let's suppose A2 is greater than 10. Then what we would need to do is we'd say A2 over, let's say, over 100, and then we would have 10 over 100. And that combination actually works well. So this is one way of modifying this circuit. So this is a workable circuit for this particular problem. Oh, here we go. So now this quantity here is in fact the numerator of this. Okay, there we go. Added that square there. All right. So this is an analog model that we can use. It turns out we don't actually have to use an analog model. We can actually use instead what is called a multirate controller. So here is our multirate control scheme. So basically we're going to trade the complexity of having an analog circuit with the complexity of using a multirate controller. Okay, so there's certain things, pluses and minuses here. All right, so let's see what's going on here. All right, so we now have M of Q tilde. So when we talk about multirate, we have two different sampling periods. TF is the fundamental sampling period, and T is some integer multiple of TF. Okay, so this number P is an integer multiple of TF. So we actually have two different discrete times going on here. We have T, where our controller is defined in terms of T. Okay, our A to D converter here is given in terms of T. Okay, and the controller Q is defined as a discrete time with sampling times T. And then I have a part in here that involves sampling times TF. So where T and TF are related this way. So notice this is a different discrete time than this is. Okay, so this is still continuous time out here. All right, so this D to A converter actually puts out values more frequently in shorter times than this guy samples. So this is the concept of a multi-rate controller. So I have this guy here now that I need to get, and now I have Q tilde. Q tilde is basically the Q transform associated with a different sampling period. Okay, so stay with me here. Okay, it's not all that ridiculous. It just looks ridiculous. Okay, so basically what happens is we take this quantity here, digital to analog converter that goes into our continuous time model, and we're going to switch it over to here on the other side, and this guy gets discretized. Okay, so it's a continuous time thing. It's going to discretize. So this is the kind of thing we need. And in addition, we have to now introduce a digital to digital converter. Okay, so it's a digital at sampling time capital T, and it's going to a sampling time TF. So this is like a discrete time zero order hold. So that's basically what this is. It's a discrete time zero order. So instead of a continuous time zero order hold, it's a discrete time zero order hold. Okay, so digital to digital converters. That's a little bit different. Okay. So in terms of what's going on here, this is slower sampling. This is faster sampling. Again, TF is the fundamental sampling period. T, the controller sampling period, is a multiple of TF. Again, the purpose of this is to still be able to apply this digitally, but to make it smoother than could be achieved with sampling period T. Okay, and if TF is small enough, all of this will act like the M of S. Okay, all of this will act like the M of S. So again, in this problem now we have Q tilde. So we want to draw a distinction between the discrete time transfer function transform associated with sampling period T and the transform associated with TF. So that's what the tilde is. That's why the tilde. Okay. So then how do we implement M? So we're going to use this form, but now we need to find this guy, M of Q tilde. And the way we do that is we make an approximation. M of Q tilde is equal to M of S, where S is some function of Q tilde and TF. And so there are a number of different approximates that we can use. One of them is called the Tustin approximation. Tustin approximation would do this. So, okay, so it involves Q tilde and TF. Okay, and so S is replaced with this quantity. So wherever we see S in M of S, we plug in this quantity, we simplify, and we get a function in just Q tilde. So by way of example, suppose this is our model that we're working with, and we want to obtain the Tustin approximation for that. Okay, so I think I didn't have this S in there. Boom, there we go, fixed it. So this is the actual function I intended, and here TF is actually what we want. TF here I'm going to set it just to equal to 0.1, just to kind of give you an idea. Okay, so wherever we see S, we plug in all of this stuff. Okay, so S squared. So we now simplify this quantity, and we end up with this, which is a fairly complicated looking function. Okay, and so this then is our M of Q tilde. So notice the function of Q tilde, it's a polynomial over a polynomial, so it has all the other kind of stuff that we like. Now, so the Tustin approximation is a standard way of doing a discrete time approximation of a continuous time transfer function. So turns out in MATLAB we have the command C2D. So for example, if I enter in my transfer function this way, and here I'm going to use a different TF, okay, 0.02, C2D of this model with TF, and notice that before we just close parenth here, but if you use Tustin, okay, so if you use, we can do the Tustin approximation, and so when you use zero order hold, ZOH, that's the default. So if you put ZOH here, that would be the same thing as what we had been receiving before without adding this extra parameter. But if you add Tustin in here, it will do the Tustin approximation for you. Okay, and then we can extract the numerator and denominator polynomials. So this is one way. This is another way of getting it. Instead of having to do it longhand, we can do it using MATLAB. So here's the MATLAB way of doing that. And so now we're all set up to be able to implement this in QuaRC. So what would it look like in QuaRC? Well, here's what it would look like to work effectively. We have to add a few extra things. So here is my motor, for example, and then this gain converts it from encoder counts to degrees. So that's what this gain is all about. So notice I'm using this block, which is an HIL read-write block. So it does a read and it does a write. Okay, and so if you click, there are actually different tabs that you can click on for the input, the output, and so forth. Okay, so I can specify in a block both an input and an output. Right. Over here, this is the M of Q tilde. Those are the polynomials that I get, M of Q tilde. I would put that in here. And then these are my three controller parameter blocks that I use. Okay. And notice I have to introduce some rate transition blocks. So this is the D to D, and notice that the D to D conversion, I need a rate transition, and it uses this kind of rate transition. Here I have this is digital, this is digital. Notice it's going to put in a 0 order hold here, okay, and also a 0 order hold here. So the blocks in yellow, I actually have specified the sampling time TF. The blocks in light green here reflect the blocks that I've introduced in terms of time t. Okay, so I colored the blocks a little bit here just so that you can see which ones are which. So in these blocks, I have explicitly set the sampling time to be t. In these blocks, I have explicitly set the sampling time to be tf. These blocks just kind of, when you insert them, they do actually, when you insert them, you won't see ZOH or 1 over Z. You won't see that stuff in there. It'll just be blank. When you build, the build will add this information. Okay, it will add that information. So in this particular block, I'm doing my control. I'm looking at both the reference signal and the output of my system. Here I'm actually taking the difference between the reference and the output. So this signal here should be going to 0. I could also put in a block here, a scope here for the control signal, or over here or here for the input to the model. So these are some things that I should see in all of it. So this signal here should be going to 0 as time, as in its finite settling. Okay, so here is the QuaRC block, the SIMULINK block using QuaRC to implement this model. So we have a way of doing that. Okay, so now we can do the robust tracking in hardware. Sweet. Well, next we're going to deal with disturbances. So here's the system that we're going to be working with. So that's the final problem that we're going to be looking at. So we're just going to touch on it briefly. So suppose you have your control loop like this, and we have a disturbance that enters in. And suppose we know something about the disturbance. In particular, suppose we know what the denominator of the disturbance. Now here I've represented the disturbance in continuous time. Okay. So in this problem, we have a reference signal, we have a disturbance signal, and so we need to introduce the model, just like we introduced the tracking model before, but now our model has as its denominator a least common denominator between these two functions. So this least common denominator is the denominator that is as small as possible that contains all the poles from both of these guys. Okay, the least common denominator. And then we have some numerator associated with that. So again, we can choose the numerator to cancel poles or whatever. There are different things we could do. So suppose we want to track a step input, and suppose we have this disturbance. So notice we have a constant which is about the same size as our signal that we're trying to track, plus this cosine. So here is the Laplace transform of this function. Okay, and I'm going to set up this model, which has the least common denominator between these two. So notice these two both have an s, and so this denominator only has a single s. It doesn't have two s's, just one. So that's the least common denominator between the two. Now suppose we have this unstable plant that we're working with, and so I'm going to combine that with the model, and I'm going to get all of this stuff. This is my discrete time model. I use this code to do all that. So here's my model, sysm. Here's the since I'm trying to track a step, I can use perf doff step for this. Okay, and so notice that when we formed this model, so this is the model, tracking model that we're working with. I basically combine the continuous time versions of the numerator of both the model and the original plant, combine the denominator and the denominator of the model. Okay, so this is like multiplying the two transfer functions together. I then take the C2D of that, and if you do C2DM, you can get it directly in terms of the polynomials, and then put those into perf_diop steps. So notice the numpy and denp here include the plant and the tracking model, or disturbance model. Okay, so in this case, my step input, my tracking signal is a step, and so I can use perf_diop step. I don't have to use RFDB_des, okay, for this problem. Okay, so notice I don't have to use a special performance program for incorporating the disturbance. I could set things up that way, but I don't need to. So it will definitely affect. So here's my minimum order solution. Here's the SIMULINK block that I can use to implement this. So here's my disturbance, here's my tracking signal, and so forth. So in this case, I'm just leaving these again as continuous time. I could also see the effect of if I put this as a discrete time thing, I could see what happens. But so for this demonstration, I just have the continuous time. So when I do the simulation, notice that I have huge overshoot, but it does settle. Okay, large control magnitudes. So I am tracking a signal at value 1, and I am rejecting the disturbance. Okay, so it is doing both tracking and disturbance rejection. So it's actually cool, but as you can see, I have a significant amount of overshoot, okay, that results from the process of rejecting the disturbance. So it's possible to change the problem in order to accommodate the disturbance, but it turns out that's not always a good idea, because even though we have represented a model for the disturbance, it's often not that precise. We don't know, for example, in our model, we assumed this, but it's like, is it really 1.03? How do you know it's not 1.05? And so basically this numerator is going to be affected by that. Okay, and so if we try to incorporate too much information about the tracking model, we might find ourselves creating additional complications in terms of trying to track or reject a specific disturbance. So generically, we would not incorporate information about the numerator of the disturbance in there. So, but as you can see, the simulation shows that indeed the system settles at 1, and so here's what notice that the input to our model goes to 0, which it should in a finite number of steps. So we've shown the implementation issues that arise from the process of using a continuous time model when you don't have, you don't want to use a ton of op amps and capacitors and creating a circuit like that really works. It can be done, but it's complicated. So here we've shown you how to work around that. Then if you happen to have a disturbance, we've shown a little bit of how to deal with that kind of a disturbance. So notice the disturbance that we're talking about, we actually have a model for it, right? We have a model for that disturbance. In particular, we know what the frequency of the disturbances are, and so we actually have a lot of information about the model. Okay, so if you have that kind of information, then you can use this. If you don't have that information, you may be it may not be so easy to work around that disturbance, to reject that disturbance. Notice the disturbance here enters in a different place than when we talked about sensor noise. Okay, this enters on the inside of the plant, before the plant, and so we are not directly getting it as part of our measurement. It's actually getting filtered through the plant before we can see anything about it. So it's a little bit more difficult problem to solve, but it is solvable if we know something about it. Okay, so in other words, it's not completely a black box. So this is the implementation issues. This is our last video. You've been a great audience. You stuck with me through the whole term. Kudos to you. Thanks for watching.